This talk has actually changed significantly since I first arrived, so I apologize for any lack of polish, but I thought it would be most useful for me to say as an experimentalist, why am I here? Why do I come and participate in conferences like this? What am I looking for? So try to give you as good an articulation of that reason as I possibly can. I'll start with what has been for me the most important observation of having to work in this field. And that is, while we're getting better and better at building little quantum widgets that can operate and do what we want, still the hardest thing there is to do in these experiments is take our big, bulky classical hands, ears, and eyes and reach down into the system to manipulate and try to measure these things. And I'll try to articulate what I see as that means for looking towards the future of the field. I'll then introduce in a little more detail some of the tools that we work with, and also some of the questions that those tools bring to my mind that I think that people in this audience might actually be able to help us with. One thing that I'm particularly excited about as a way to address this problem is that, if classical interactions are the hard thing, what can we do if we take as much of the classical hardware out of the equation as possible and try to do as much of the manipulation, maintenance, and feedback on these quantum systems as we possibly can down at the same quantum, or at least very cold level that the experiments we're manipulating are. The last two parts will be me showing you an example of how I try to put my money where my mouth is in thinking and applying these basic motivations towards one of the projects we're currently working on of developing an alternate technology to make a microwave circulating element that could live down with the other hardware that we're building. So the vast majority of quantum engineering proposals look schematically like this, where you have some big classical external agent that's given access to a set of actuators and a set of detectors. And they have to reach all the way down into your experiment, where if it's a superconducting microwave experiment, say, it's going to be in an extreme environment. In particular, it's going to be usually at something like 20 millikelvin, whereas all this other stuff is almost always at room ambient temperature. To take a little bit more specific picture of what I mean by that, this is a picture of a completely empty dilution refrigerator, or at least the insert of it that our experiments happen in. And our experiments have to be at the very bottom of this, down where it's 10, 20 millikelvin. Although there's all these cold stages in between, anything that's not significantly less than a quarter Kelvin, say, when you're working in the 48 gigahertz band, is pretty classical. So it doesn't just have to be cold, it has to be extremely cold. And another thing to keep in mind that will come up later on is that not only are these stages characterized by different temperatures, they're characterized by different amounts of cooling power. The amount of power that this top plate can absorb, it's at 55 Kelvin, say, is something like 50 watts before it starts to heat up. Whereas down here, where the experiments actually happen, the cooling power is much less than 200 microwatts, actually. So it can handle a lot less dissipation. And the main problem is that it's hard to go between these two things. How hard is it? Well, this is a schematic taken from the supplement of a recent superconducting microwave qubit feedback paper from the DiCarlo group that we help participate by giving them this one little box there. But it's an important one if you know the field. This is an experiment that was trying to feed back and control this transmon qubit. But if you actually break the schematic down into what it does, this is the feedback. That's the thing you're trying to control. And then there's a little bit of open loop control and stuff. The vast majority of the hardware required to do this is in the feedback. And it's all very classical hardware, except for the special box we gave them. And it's not just a lot of big, bulky stuff that has to go between all the temperature stages. It's just, frankly, expensive. This little squiggle there, that's a $35,000 squiggle. That box there, that's a $50,000, $60,000 box. There's another one, 10,000, 10,000, 10,000, 5 to 10,000. It adds up really fast. And what this means is that in many ways, the primary impediment from going from, say, just one of these qubits to maybe 10 of them, not an extreme number, it's not producing pretty good qubits anymore. We're pretty good at that. it's more and more the fact that we would have to reproduce all this big, bulking, expensive classical stuff if we're going to go about things in the way that we have been doing so up to this point. But there are other ways, at least potentially, and that one thing you can note is that you can think about just having multiple circuits that live down at the same cold environment that are just physically connected to each other and that share continuous signals circulating between them that are always bouncing around in cold temperatures, that are always bouncing around through the same environment. So things happen faster, they're more compact, and it's also cheaper. It takes a lot of resources to develop some of these circuits in the first place, but once you have a design that works pretty well, the reproduction of those circuit types is a lot more efficient than reproducing all the classical stuff. I want to point out that while this talk will be about microwave systems, I did my PhD in AMO quantum optics, and I believe the same thing is basically true there in a lot of cases, where you might have atoms or ions that are living in, that you're experimenting on, and they're going to be in a vacuum chamber, which is very different than the ambient environment of the lasers and the detectors that everything else are in, typically. One of the experiments that convinced me of this fairly early on came out of the Kerckhoff group. And what they did was they actually used 2 qubits, maybe this one and that one, that was on a single chip to do quantum error correction on a 3rd qubit that was on the same chip without any measurement having to be involved during the process. Using an algorithm that I think was inspired from the ion community, they just took that 1 qubit state, separated it into 3 guys, errors happened, and fed it back. And this is a superficial observation, but I think it's an important one, that this quantum error correction actually appeared in the literature before any of the basic, very classical measurement-based feedback stabilization protocols happened elsewhere in the community, which to me suggests that this kind of measurement-free approach can be an extraordinarily natural way of doing things. If you look outside of the quantum computing-inspired community, you can actually find much larger scales of integrated superconducting microwave technology. For example, across the road at NIST from us, there is a large group that builds superconducting microwave detectors for things like they go in telescopes, or they drive them. You can drive them next to an Iranian nuclear facility and see if what you think is in there is actually in there. Things like that they're used for. But what it is actually a camera full of a bunch of 32 by 40 pixels of squids. Here's sort of a simplified electrical schematic of what's actually in there, where you have a whole array of these squids, which are these little loops with X's in them. Now, I've heard it described that the problem in building something of this scale is managing the number of connections between cryogenic and room temperature. And for example, where this bottleneck comes in is that each of these squids, it's actually a nonlinear detector. And so in order to linearize it, in principle, each one needs its own little feedback loop. 32 by 40 pixels with feedback, that just was not going to happen for making a usable device. So what they decided to do was to multiplex the feedback, so you'd have one line for each column, but then you'd only read out one row at a time. And so the feedback would just have to work on one guy at a time, and then you go on to the next one. And so it meant that the vast majority of the time, each pixel was actually turned off. Wasn't working at all, but that was the sacrifice that was worth making if you could reduce the number of feedback lines to room temperature by a factor of 30. That still having to rely on feedback to room temperature is a severe bottleneck, and in the future, they actually found a nice open loop, infinitely multiplexable way of linearizing all their detectors. I think there might be a sensitivity sacrifice, but they're going to that model in the future so they can get their wire count down to from room temperature down by another factor of 30. So, but you're not always going to find some open loop, infinitely multiplexable solution to your maintenance problems of circuits that are operating in these extreme environments. You're always going to want to have some sort of feedback control, most likely. And so I think it makes a lot of sense to start thinking about, well, what kind of maintenance and manipulation of the systems that we're interested in building can we build that live in this extreme, typically very cold environment? They're embedded as close as possible. They might not be doing very spooky quantum mechanical things. They might be doing classical information processing. But they have to live in a cold environment, and so there are all sorts of constraints that come up from that. They can't dissipate a lot of power, for example. So it means that they're probably going to have a large degree of coherence inside of them. They have to probably be built out of the same superconducting technology. That induces new constraints. And some of the things I look to for this, from this community is ways of thinking about how I might go about modeling quantum compatible technologies for enabling sort of cryogenic closed loop systems. So with that overview, I now want to give you a little bit more detail of the sorts of circuits that we work with and the sort of things that are familiar to us and that work well. And then what I think what that means, I think, looking to the future. A lot of the circuits sort of start out as passive circuits. One very common passive circuit is an LC resonator, which involves an inductor and a capacitor. This is what it looks like. This one was made out of aluminum, which is the whitish stuff, and the blue stuff is, I think, silicon here. The inductor is a big spiral. These two little circles are actually two plates that are on top of each other with a separation. And then you have a transmission line that's coming down from here that couples inductively into that. Now, the nice thing about these microwaves is that there's actually lots of optical analogies you can make to the technology. And in this case, the probably closest optical analogy would be something like a microdisc, where you have resonant modes around the edge, and then you have a fiber taper that's coming down through the middle. You can do other things. For example, you can take more inductors, more capacitors. You have 4 transmission lines coming in here. And these guys are forming now a bunch of T filters. And if you set the impedance of each of these right, you create what's called a 3 dB hybrid, which is a passive circuit that if you send a microwave tone in here, it'll be split this way and that way with equal amplitude. Sort of like coming in through here, it'll be split, I think, here, coming out there and there. The optical analog here is like a 50-50 beam splitter. When you're talking about control, what are the knobs we have available to us? Well, one of the primary knobs that we have available for external control is a squid. A squid is 2 Josephson junctions, here indicated by these little X's, with a superconducting loop around them. And a DC squid like this acts like a tunable nonlinear inductor. It's tunable because if you try to apply a magnetic flux through this loop, that will change the critical current of this squid, the critical current being the maximum current that the squid can support in its superconducting state. The actual critical current depends on that external flux through a sinusoidal invariant parameter. This is important because the effective inductance of this squid depends on that critical current. And it's a nonlinear inductor, like I said, so the effective inductance actually depends also on the current that's currently going through it. And so to lowest order of nonlinearity, you can actually write this dynamics out, and it looks very much like a linear inductor plus something whose optical equivalent is a Kerr nonlinearity. The important thing here is that with this external knob of external flux, both of these things become tunable because the critical current appears in both of those terms. You can take those tunable elements and put them together and get tunable components. One circuit that we like a lot is this thing that has been called various things, but now it's called a tunable Kerr circuit. What it is a capacitor up here, there's a capacitor there, and a series of array of about 40 of these squids. These things act like inductors. There's a capacitor. You have an LC resonator. If you apply flux to this thing, that inductor becomes changeable. So if you apply a flux here, you're changing the L in an LC resonator. That changes the center frequency. And you can do so over about an octave, again, in the 4 to 8 gigahertz band. And actually, the main reason why this thing was developed in the first place was not for its linear characteristics, but for its Kerrness. But I'm not going to talk about that much here today. But its optical analog would be like having an optical cavity with a Kerr medium in between. And if you apply this flux, that's like changing both the position of that mirror and the amount of nonlinearity. You can take those components and integrate them into networks. in sort of a modular fashion. You can do that either on chip or you can do it off chip. Off chip, I've put some of these things inside a little gold box or another little gold box, and you connect things up with coaxial cable. There are different advantages to both approaches. This guy, it's smaller, you can mass produce it, but you can't test the components individually. Here you can. You're also going to have less crosstalk, but it's harder. You're going to have more loss, and it's harder to make a billion of them. So the things that I try to think about when I'm designing an experiment are, well, this is extremely vague, but the cost is the more important thing, I think. I want to manipulate, characterize, and maintain a quantum circuit while minimizing the number of components I have to use, the number of times I have to cross temperatures, the precision with which my components have to have particular parameters, the precision with which I have to know what those parameters are, and I don't want to have to make anything that I haven't made before. That takes a lot of time and money. So really, I'm not, for the most part, starved for data or signal-to-noise ratio for these networks, really more starved by what sort of hardware we have to use. What do I mean by not starved for signal-to-noise ratio? Well, until about a year and a half ago, our group had no qubits whatsoever. We're kind of an anomaly. But now they've gotten so easy and so good, we're like, why not? But in that amount of time, our ability to distinguish between a qubit in one state and a qubit in a zero state looks something like this. Optimal filtering theory, the marginal benefit for applying that to a signal that it's not great. So it's not a priority at this stage. If you open an electronics textbook, so the question is like, so what are the basic modules for what I do? If you open up an electronics textbook, you might see a discussion where they say the fundamental components of electrical engineering, lumped element components, for linear, passive, constant, and reciprocal systems. That's a constant thing, a similar thing to think about. Are things like resistors, a capacitor, an inductor, and transformer. This list can be modified. If you cross that guy out, you can actually induce, you put in this thing called a gyrator, which interestingly allows you to cut these two things out. Linearness is kind of boring, so if you get rid of that, you're going to need some nonlinear element. For us, that's always going to be a Josephson junction. And for our sort of things, you typically don't want to dissipate a lot of power, so you're not going to have a lot of resistors in them. But really, if you look at the vast majority of work in this field, these are not what you see sort of in the schematics. What you see time and time again as the effective modules of superconducting microwave technologies these days is probably something like this list. Some people might have other things added to this list. For our group, we might put things with little mechanically wiggling things in it. But I think this is a pretty good summary that most of what you see. They include things like qubits, but maybe even more commonly these days, you don't just see bare qubits, but you see qubits embedded in some sort of resonator, so-called circuit QED. There are transmission lines, there are splitters, there are amplifiers that involve Josephson junctions, and there are circulators. And so the questions that I have, working in this field is like, are these really the things that we should be working with? Should we be doing everything with these things? We've done a lot with them, but is that all there is? It seems kind of restrictive just looking at it. If we're going to be doing both quantum and classical information processing cryogenically, should we be doing both types of information processing with this same set of stuff? Or should they be different? There's arguments you can make both ways. If these are the modules, how do we model putting these things together? We've talked about a lot of different ways of doing it. The vast majority of the ways it's done, especially for experimentalists, you just use your intuition without any really formal construct. You can think about instead maybe that all the qubits are spins and they're coupled together. SLH is nice here because each of these things actually fits directly into a quantum optics type picture. You could think about having a Lagrangian for the whole thing and analyze it that way. But really, these things are electrical circuits. And the extent that you see electrical circuit theoretical concepts appear at the level of the publications and not that's buried away in the supplements is quite minimal. But you really should be thinking about, analyzing these things from the perspective of two-port networks, circuit graph theory. There's a bunch of different options there that are probably underutilized. So what are some of the advantages for doing processing cryogenically? That's what I want to, in my opinion, articulate to you now. One of the main ones is probably going to be a bandwidth advantage. In any experiment, even ones that don't close the loop up here, look like this to date, basically. You have something you're measuring. You actually have to home build a amplifier that either achieves or comes close to achieving the fundamental quantum limit for amplification of electromagnetism. And then that gets a little bit hotter and it goes to this commercial thing called a HEMT amplifier, high electron mobility transistor. And while it's very good, if you turned its noise floor in terms of quanta of energy, it's something like 20. Now, what that means is actually this thing throttles the bandwidth in the system indirectly. Because it has that relatively high noise floor for doing quantum-y stuff, in order to set the noise floor to be something that's shot noise limited, you actually need something like 25 dB in this preamp. And to date, all these preamps come with a gain bandwidth product. That is, the best ones have something that's sort of in the low hundreds of megahertz range, which means to get, see sort of quantum shot noise in a single shot, you need this much gain, which means that your bandwidth is going to be limited to something like 10 megahertz. But if instead you close the loop fully cryogenically, you never have to go to that noisy amplifier. In principle, you could have fully shot noise limited feedback in this entire loop. You could exploit the entire gain bandwidth product in this loop. You might not need 25 dB in your feedback gain. You could get away with 10 or maybe even 2. So there's more flexibility there. Another advantage for doing cold processing coherently is that you have a lot more control over where you actually put the dissipation. Power dissipation is critical in these extreme cryogenic environments because the fridge can't support a lot of dissipation. For example, a classic, basic element of digital information processing, classical information processing, is a set-reset latch. It's 2 NAND gates with some interesting feedback there. A few years ago, I did an experiment using these magical TKCs, some hybrids and some directional couplers that actually acted just like a cryogenic set-reset latch. But each of these things individually should have no dissipation. Digital information technology in cryogenic systems is nothing new. I think even going back to the 60s, people were at least thinking about, if not already doing, information processing using what's called rapid single flux quantum. The distinction here is where's the dissipation. In my case, the dissipation that allowed this thing to latch actually happened at a higher temperature. The output of here went to resistors that I put at the 4 Kelvin stage, the hot temperature stage, because that's where it could handle a lot of power dissipation. So that's why I put it there. In RSFQ, the dissipation happens through resistive shunts that are embedded directly across those junctions. And for systems of significant size, this starts to heat up. This exact problem is also a problem in the large-scale superconducting detectors too. The other advantage that I've talked about a lot already is this notion of cheapness. So if you're trying to control one of these qubits with one of these amplifiers and using all this stuff, buying a whole new set of these, it takes a lot. Whereas I can, and I've done experiments, if you were at Praxis last year, you probably heard about this one, where I have one circuit that I put here, I have another one of these circuits that I put there. I just connect them with a T, and that actually creates a feedback interaction between these two guys. It looked like this. And what I was able to achieve by closing the loop cryogenically is I got a new effective closed loop system that was far more flexible than any comparable system in our field of electromechanics had before. Namely, I had the ability to dynamically tune either both the bandwidth and the rate of dissipation in this network on very fast time scales. I could also, because this amplifier does some squeezing, squeeze the mechanical motion of a little widget that's inside the circuit. And I got that at no extra cost, essentially. We already had these things. We were already going to use them in any other experiment we were going to do. If I just close the loop with a little t, I got all that stuff for very little. I got that stuff very cheaply. Let me just try to hammer this point down even further. This is what you do in classical electronics. If you have an op amp, it by itself is a gain 1 million amplifier. But if you take another standard resistor and loop it around that amplifier, it becomes a very different amplifier. And you can choose its gain by choosing that amplifier. It's a lot, and so essentially you get a new type of instrument, but you get one without having to go back to the fabrication facility and make a precise 3.5 dB amplifier. What you don't do is you don't measure with a computer what comes out of the amplifier, calculate the optimal optimal estimate of the state, and then feed it back. You could do that, but in a lot of cases, you don't do that. Complex modules can be okay. This little triangle here, it might look something like this. This is actually a fairly big op amp. You can get them a lot smaller. And it's not the cheapest op amp either, but it's yours for a low price of $425 at westfloridacomponents.com. But what's actually under the hood there is a very sophisticated and interacting network of a bunch of transistors, resistors, and capacitors that are all in here that, through the magic of capitalism, because they knew that people were going to use these modules over and over and over again, they could make them cheaply and robustly for us. So why in my experiments do I keep using these things? I mean, they look like this. It's a rather sophisticated piece of microwave technology. Well, it's because they're like our op amps for our experiments. This is a terrible picture, but each of these little shiny squares, like the one that's in this green thing, is a chip. And all of these guys are less than half of our last run of JPAs, or TKCs. There are actually 4 of these things on a single chip, and so far we have 100% yield. I don't think we've measured a bad one. So we're swimming in these things. We have far more of these things than we have $35,000 amplifiers. So I would like to be able to use them as much as possible. So now I want to step you through, in the remaining time, how I think how these sorts of background motivations is particularly inform some of the experiments that I'm gearing up to do. This part will be me thinking about how I might be able to realize an alternate technology for making a circulator component, because that's kind of the weak link if you're in the field of all these things. And I'm going to show you how I think about this problem of making such a network using both intuition and actually using what I found to be quite convenient, an instance of electrical engineering graph theory, and then turning that into an SLH type model that I'm, and many of you might be more familiar, comfortable with. You can write, so if you just have, let's just start with a more simple electrical schematic system with a transmission line, capacitor, and inductor. You can derive the equations of motion for something like this, sort of I've written it out here, where we're talking about what is the dynamics of the charge on that plate and the magnetic flux through that inductor, so that's the change, as driven by input currents. And then you can also relate outgoing currents according to those 3 things as well. What's important to note here is that say this inductance L actually appears in both Hamiltonian type dynamics and dissipative type dynamics. The center frequency of this resonator depends on L. Also, the impedance of this LC resonator, which determines how quickly it dissipates in the transmission line, also depends on L. And so if L is the tunable thing here, in this simple circuit, if you tune this, you're actually going to tune both of those things simultaneously. Now, in experiments I've done thus far, I've been blessed with a large amount of modularity. So in this experiment with the mechanically thing, I had basically 3 components, these 2 circuits and a T. And I could think about it as a series of 3 input-output models that are continuously exchanging microwave fields. Now, what was nice here is that each module either had a resonant internal degree of freedom or it was a completely static scatterer, like this intersection of transmission lines. And in that case, I can pretty directly apply SLH-type formalism because each of those things individually has a very nice quantum optical analog for its model. And in this experiment, I tuned, and I wanted to tune simultaneously both the effective dissipation of this guy through this output port, and I wanted to tune its effective center frequency at the same time. And I could do so by tuning that circuit. So that I could, if you're looking sort of at the reflected phase coming in here, I could either have a resonance that was narrow band and relatively high center frequency, or it could be broad and low frequency. And that's exactly what I wanted, so that was fine. But in most cases, a more independent tuning of both things would be very nice. Okay, why do I care about circulators? Well, we use them all the time. Now, this schematic that I've shown you a bunch already, just to manage one of these transmons takes 4. They're there because it's important to enforce one-way flow of information. So what it is it might be something like this, where you send a signal in here, and then it comes out there. You send a signal in here, and it comes out there, goes out there. And it's particularly useful for protecting circuits from back reflections. But they are commercial components. They're relatively large. They have big magnetic fields, like 10 Gauss or so, and so they actually have to be even like feet away from your superconducting components. They're fundamentally non-integrable for that reason, and they also, these things are often the main source of loss in experiments. So how might you make a more quantum engineering compatible circulator? Okay, so now this is the intuitive part. It involves a large amount of magical thinking that I then turn into something that seems more realistic. But let's start with the magic. And this is the first time I've struggled with trying to explain how this works. So let's see how this goes. Imagine you have a transmission line whose center pin comes out into a loop like this. You can also imagine then there's a little floating circuit in the middle of that loop that looks like this. Now, if you send a current through this loop, it'll go around the edges. And as soon as you turn that on, that will try to induce eddy currents inside that floating circuit. It'll go like that. Alternatively, if you could magically induce a current in that floating circuit, that will induce eddy currents in the external field, which, if this transmission line is terminated with a resistor, say, would start to dissipate that electricity. But it's important how this circuit is oriented. If instead it was oriented on its side here, actually you should get no eddy currents flowing from these guys, because now the net magnetic flux into this top loop is 0, whereas before it was non-zero, because they're oriented this way. So that's the case there. What the next step of building this up is you can imagine now attaching another port to these two lines here. If everything just stayed like this, you send a signal in here, you actually would get no signal coming out this port because the potential at both these points should be exactly the same. But, okay, now here's the magic. If you can imagine, if you induce eddy currents inside this guy through the signal here, just rotating it physically really fast, much faster than the eddy currents can dissipate, that will then induce signals in this external loop that will want to flow this way and will be transferred to that external port. So you've sort of transferred signals. This, of course, can go both ways. For example, but maybe it's easier now to think about a slightly modified floating circuit where now you have another connection going from here to here. Critically, there is no electrical connection in the middle there. That's why there's no big black dot. Okay, so now if you send in a red signal in here and a blue signal in there, it'll induce currents in that guy. If it now rotates, those currents you'll transfer blue to the red side and the red side to the blue side. But note that it's important that the phase with which those signals got transferred, the blue guy going to the red side, it actually now opposes this incoming signal, whereas the red guy going to the blue side actually works with it. So there's a 180 degrees phase shift depending on which direction it's going. This thing is what's known as a gyrator, which may be unfamiliar to people with physics training. But actually, in this case, in this picture, because both of these ports have to be floating relative to each other, that's a little awkward to do. So let's break it up. You can imagine having now sort of a balanced drive of this circuit, where I now have two ports on either side here that are both, these can have the same reference. And if we have two sources on the input here that pushes and pulls down there, you get exactly the same situation that I had in the last slide. And it'll do exactly the same thing. You can make this thing look like a gyrator. Now, this way of driving this system, where you push here and you pull there, you think of it as sort of odd mode driving of the system. You can also think about driving it evenly, where you push on both of these cases. And if you work through it, you push both here, signals go in like that, and they go out there, and they go out there. Critically, though, that actually doesn't induce any eddy currents there because, while current will try to flow like this, because there's no connection there, no current, the charge can't go anywhere and it doesn't flow. So even if it spins, nothing changes. If you superimpose these even and odd mode solutions, you figure out what happens when you just drive on this one line. And if you do that, work through it very quickly, you see, well, when this thing spins, all the signal goes out just there. Or if you drive here, all the signal just goes out there. And it keeps going around in a circle. So really, this magical thing, should realize a 4-port circulator if you could make that thing in the middle spin. The same principle would work if this guy instead had a bunch of inductors and capacitors, and it would work at the frequency with which the impedance of the modes looked like it was 0. All right, you have to watch it spin again. Like I said, it's kind of rough. Okay, so how on earth do you make something like this? How do you make a circuit hardware spin? And then if you can think about how you might make it, how might you actually model that thing? And it's important to know how to model it quantitatively because you have to answer questions like, how fast should it spin? Clearly it has to spin a little bit, but if it goes too fast, does that screw everything up? I don't know. So now we have to get a little more serious. So how do you realize a pure bipolar switchable dissipative circuit? Something like this, and are we going to watch it spin again? Yeah. Where we allow ourselves now the ability to have tunable linear inductances. Well, taking cue from the Deveray group, who first started doing this seriously in recent years in our community, but really they're everywhere in electrical engineering. Bridge circuits here should work very nicely. In that if you think about building a circuit like this with a capacitor in the middle and inductors here, you now have a resonant mode like this, and you have an itinerant mode that comes out here and goes around like that. In the case where each of these inductors are exactly equal, these 2 points will always be at the same potential, and so you'll never excite that resonant mode. It's really like sort of having a floating circuit oriented like thusly. But if you have the ability to imbalance these circuits, then you can start to excite that resonant mode. What's important here is that both the phase and the magnitude of that coupling is now dependent on this perturbation parameter delta, and actually the center frequency of this resonant mode is independent of that delta. You're able to separate dissipation from center frequency because it's independent because the total inductance presented to this capacitor is actually now L if you add all these things up in series and parallel. You can then, okay, we like modularity. Let's add another bridge and we can add another port. And now if the dithering of these inductances now varies, goes as something sinusoidal, it can be like having this thing sort of rotating at some angle theta. It's a technical point, but it's important for superconductivity that you can modulate this thing in different ways. If you double it again, you add another resonant mode. So you not just have your capacitors going this way, you also have capacitors going like that way. You do all the dithering right, it would be like this picture of our magically derived circulator. Okay, but okay, so now I have a better picture of the hardware of what I might actually want to build. How do I make a mathematical model of that? Well, one thing I want to note, especially for this audience, is this is, again, a highly modular network. You see these things all over the place. And you see this thing doubled again, every once in a while. But I want to be able to derive the model dynamics using something as algorithmic as possible. In this case, in the ideal case, I could honestly just guess the answer. But when you actually have experimental imperfections, your intuition is going to break down pretty quickly. And the important thing, I think, talking to a lot of optics people, or people who tend to have more optics-y backgrounds, is that these modules in this case don't no longer by themselves fit into a quantum optics picture. This inductive bridge, it no longer has a resonant internal degree of freedom, nor is it a completely static scatterer. Because it's a bunch of inductors, different frequencies will scatter differently. And so it doesn't fit into, immediately into sort of the picture of either things that are like optical cavities or things that are like beam splitters. Now, how you can analyze this, you can use lots of different approaches that are from, especially in electrical engineering. Maybe a two-port network approach would be the most usual thing, but actually for me, what I found for this project of just trying to get a model out in the first place to be the most flexible approach, I used just an eensy bit of graph theory, that I was inspired to sort of develop this thing by some work that was done a few years ago by a bunch of people that used to be at IBM. And what I wanted was a way to get a model that would get me to a quantum optics type model as quickly as possible. So I'll step you through how that worked for me, at least. There's by no means a general approach, but I think things like it maybe could be generalized. You first choose for each of the branches a direction of current that you define as positive. You then choose a spanning tree that's you indicate branches, this guy, and that guy, that touch all the nodes in the circuit but make no loops. The remaining connections are not in the spanning tree. With this tree, you can now identify what are called fundamental loops, which are loops that are all linearly independent, and that any other loop in the circuit would be a linear combination of these. And in each of these loops, Kerckhoff's voltage law would have to be satisfied. And you can actually sort of write that as a matrix equation where you have the tree voltages on one side and you have the non-tree voltages on the other side. And they're related through some matrix that I call F transpose, which is full of ones and zeros that encode the connectivity here. Now the magic is that once you have the voltage laws, you also have the current laws. And this is through the magic of graph theory, is my understanding. Essentially the current laws identify for you a bunch of cut sets that are barriers that partition this graph into two parts through which the flux of charge has to be zero. And so that lets you write using the same F all the current relations. Now, it's very easy to, at least in the frequency domain, write down an input-output model for this circuit where you have input fields coming in there that drive these tree currents and they're related to the output ones. You can then solve for the one you care about, which might be this one. Then if you wanted to turn it into a quantum optics model, you have to start making some more approximations. Particularly, you make a high-quality approximation, namely that this mode you care about is much lower impedance than the external field. You then put it back in the time domain and make a slowly varying envelope approximation to get a time domain dynamical equation of motion for this system that is compatible with the quantum optics picture. And what it is that you say some variable AC, which is related to this current, is driven by A in, which is related to this current coming in here, and tells you what the current going out is. Now, for my case, if I plug in sort of the perturbed inductors there, I get a bunch of deltas. But critically, those deltas appear only in the coupling terms between the external and internal degrees of freedom, and in the dissipation term for that mode. They do not appear in the Hamiltonian, just as you would expect. For me, this approach has been sufficiently scalable. And what I wanted was a way of modeling this thing, and that I can choose a spanning tree. I can identify all the loops. Here's one of them. Here's a cut set. And from that, using a very ugly, just lazy Mathematica code, I can get an input-output compatible model that describes the circuit, where I'm talking now about the dynamics of current through that capacitor, that's A1 and A2, and they're driven through input signals going in each of these ports. And that's so A1 and in, so A, B, C, D, in. And the important thing here is that if you dither these inductances in the right way, that appears only in the external coupling. And once I have this model, the reason I like it, I'm familiar with it, but also it allows me to analyze and answer questions like, well, how fast should I spin this thing? If you make theta now dependent on time, like it was spinning, you see very quickly that if you adiabatically eliminate these internal modes, that means that input signals are within the bandwidth of the circuit, and that when you set that rotation angle to be exactly equal to the total dissipation of each of these modes, that kappa up there, this thing becomes exactly a 4-port circulator. So if you send a signal in here, it goes out there. Send a signal there, it goes out there. That's a high quality approximation. As someone who wants to actually build something like this, that's great, but I want something that can be more general, that can take care of cases where there's loss, or that I want the bandwidth as big as possible. So I can do a full time domain circuit simulation. I probably can't see this too well using Simulink and MATLAB, where I just draw my circuit, and now I'm thinking about modulating the inductances in each of the inductors, like that, and a bunch of sources. And I choose parameters which for us are quite reasonable to choose for actually building the circuit. And in this full circuit simulation, I can, it basically confirms the high Q estimate that when I set a particular parameter for the rotation angle, if I send signal in here at the blue, it always comes out C in the pink. If I send in signal C in the pink, it always comes out B in the red. So it should circulate like that. We're now at the stage of laying out the hardware. It's not quite the audience, nor do I have the time to go through all the design questions that come into this, but it has a lot of nice features for us. It's about 50 megahertz bandwidth. It should have a very tunable center frequency. It should have a high saturation power because we want these squid arrays to be linear, not nonlinear single squids. Very important for a superconducting circuit to be gradiometric to external magnetic fields. Although there are 16 squid arrays, you only need 2 biasing lines to do the important biasing. And that biasing is very slow on the scale of things. It's like 50 megahertz. Again, it's the same frequency as the bandwidth, which means that both it should be very easy to separate from the carrier tones, and that if we wanted to distribute that modulation over a significant spatial difference, that should be a lot easier to do at low frequencies with large wavelengths than for high frequency things. And also this notion of modularity, this is part of the project, got funded by the ARO, that we said we would do a bunch of things, and it was important to find modules that could do multiple things. And these bridges are our solution to that module. Now I'm using Conrad slides because, like I said, not polished. But you could think about having these bridges sort of put balins around them so you float them right. Now something like this, if you bias it one way, you transmit with one phase, bias it another way, you invert the transmission. And you can imagine having time domain CDMA multiplexing of multiple qubits, say. Where you have a bunch of qubits here, you have now your modules that we're going to make a bunch of, and if you pulse them with Walsh codes, you should be able to read all these out simultaneously with a single source. So that's about the right time to conclude. The main points I want to leave you with here today is that, in my opinion, measuring things implies that there is a really fundamental mismatch of hardware and in homogeneity. That makes things difficult usually. So to me, that suggests that maybe we should do more processing of our information in the quantum world. It doesn't have to be quantum information processing, but it has to. But we want to do the stuff that you'd have to do anyways to support the experiments that you want to do. So one of the questions I keep asking myself is, what are the circuits that I should be getting really good at building and be using over and over and over again? Because if I can identify those, I can do a lot more than if I have to make a new type of component for each thing that I want to do. If you do this, you can think about really taking control of dissipation, which is important because you have to put it where you want. You don't want to heat your fridge up. And you can do cool things with it, like making circulators, like I talked about. And then for me, one of the things that makes me comfortable and I think could help out analyzing these systems is to go go from Kerckhoff's law's descriptions of larger scale networks like this to other ways of representing these sorts of networks. Especially for me, I like thinking about things sort of in optics terms because that's how I grew up. With that, I'd like to thank you all for your attention, as well as all these wonderful people. Conrad's been a wonderful supervisor. We complement each other in such many ways. I just hired a great student, Ben Chapman, a lot of other great graduate students. Alexandra and his student Kevin actually happened to be visiting, coincided with the main ideas developed here, and Kevin's been helping me out think about this. And then all the people at NIST who really are, are such an important resource for us when we're thinking about doing now larger scale integrated microwave technologies. And like I said, these are some of the funding agencies. So thank you so much for your attention.
Questions? So I have two questions. One, when it comes to the circuit design, of course, electrical engineers have spent a long time working with parametric circuits. And I'm kind of curious why the toolbox that they have is not the one that you're using.
Frankly, it's expediency in my background. I have a degree in literature. So I came to this world through optics. And for a lot of us working in the field, there's a lot of optics people now, but the vast majority of the physicists who are the ones that are interested in the experiments, they came from condensed matter usually. And we are not as facile with what tools are available in electrical engineering. And nor do those tools always have, they're usually, they are more general than the sorts of circuit components that we allow ourselves to work with. Basically, we allow ourselves to work with Josephson junctions, capacitors, and inductors. Whereas if you use many of the tools in the engineering community, they're built for far more flexible things. So it's a combination of both who they were built for and our specific background.
But you do use a lot of transfer function analysis methods, don't you?
Oh, absolutely.
So that's part of
yeah.
that.
Yeah.
Yeah, but that being said, this IQ approximation, for example, is something that.
Oh, absolutely. I know some. I don't know everything, and I have to produce results, and so I do what's fast, and that works well enough for me. So that's the real answer.
I guess the other question is, given that you're coming from this sort of Wheatstone Bridge picture.
Yeah.
Wheatstone never made into the slide, but.
Oh, it's so.
Coming from the Wheatstone Bridge picture, when you look at what Deborah is doing, the crucial point is that you have a very easy method of frequency conversion.
Yep.
And so I'm kind of curious why you're so wedded to single frequency reciprocity.
Because having slow modulation has a lot of nice technical benefits too. You don't have to make sure that you don't have to first synthesize all those sources usually, and if you want to think about distributing these signals that are doing the crucial parts of your experiment over a larger scale system, if you have longer wavelengths, that's easier to do. You don't have to worry about the relative phase. When I put it in here, what phase it will be. If I put it in there, what phase it will be. And also, if it's low frequency, it's much easier to filter out the sort of modulation tones from the main carrier than it is, say, in the if you were doing a Deborah type frequency conversion. In his case, the pump tone is just a factor of 2 different in frequency, roughly, whereas in this case, the modulation tones is a factor of 100 different from the carrier tone. So it should be much easier to separate out.
Correct me if I'm wrong. I thought your bandwidth and your tone were essentially linked.
Yes, but the carrier tone you don't want so. Huh?
So omega kappa that is roughly equal always, right? For your system.
Yes, but the carrier tone you don't want.
No, I understand.
Okay.
I'm saying I could have done a Deborah style experiment, but rather than frequency converting from 4 gigahertz to 6 gigahertz, frequency convert from 40 hertz to 4.05 gigahertz. Right.
But then, in order to do that, you need a tone that's at 8 gigahertz.
No, I could have done that with a 50 megahertz tone.
Is that correct?
Yes.
Okay.
I've been looking at this
Yeah. Okay. Sure. Yeah. But another thing that we like doing it this way too is that we're allowed to, we use, because we want, our group actually works at higher powers than a lot of other microwave groups because we do mechanics stuff. We want the handling power for these circuits to be as large as possible. And so working with arrays that were essentially linear, that you could do the modulations for this external slow flux was a very nice feature for us.
Just a good question.
Yeah.
The device is active, if I understood correctly.
Mm-hmm.
Pumping it. Where does the energy of that pump go?
Well, so that's an important point, but you would want to return it off chip. So it's not dissipated on chip. It comes in here and then goes out here, and you would send it up probably to a reference that it's at the top of the chip. Sorry, the top of the fridge.
Have you looked at how would the non-classical state traveling through the device would be influenced by the dynamics inside?
Using my intuition that everything here is linear and non-lossy, I think it shouldn't change it very much at all. Going from a linear system with no loss to the quantum mechanical picture of it, you should just be able to turn all of the complex numbers, amplitudes into operators, and it should go through. And because there really didn't look like there was a lot of, if the signal is within the bandwidth of the circuit here, there wasn't a lot of distortion, I imagine it wouldn't be perturbed very much. So if I had the time or an interested theorist, it'd be a nice thing to work through properly, though.
Actually, this is where the black box quantization procedure would be really useful. So you hand someone an impedance and they can do that.
Mm-hmm.
Right, more questions? Okay, so let's thank Joe again, both speakers this morning.